All right, we shall get started. Okay, well, I appreciate everyone's flexibility in meeting online today instead. And today we will continue looking at numeric optimization methods. And the method we're going to look at today is the Nelder-Mead method. Okay, the Nelder-Mead method is a numeric method for finding the minimum of a multi-dimensional function. So think, two-dimensional or higher. Okay. And it is what we call a direct search method. It does not require us to calculate derivatives. Instead, what it does is it calculates the function at a few different locations. And depending on the values of those locations, it selects a new location. And it continues to do this until the algorithm basically reaches convergence. But the algorithm is basically instructions for how you go about looking for new directions or new locations to search. And then you continue to evaluate those locations until you're reasonably confident that you've reached a minimum. So, the way the Nelder-Mead method works is that it uses a simplex. A simplex is basically just a shape that has one more vertex than the number of dimensions that you are in. So if we're in a two-dimensional space, a simplex is a triangle. It has three vertices in a two-dimensional space. Okay. In a three-dimensional space, the simplex will have four vertices. So it is a tetrahedron. Basically, just imagine a kind of a four-sided pyramid, basically four triangles together to make a pyramid. If you're in a higher dimensional space, like if you're in four-dimensional space, then you have what's called a five cell, and a five cell it's hard to visualize, but this is um, a four-dimensional, basically like a pyramid, but it exists in um, five dimensions. This is just a rotation of a five cell. Okay. These are just more of these different kinds of uh, rotations. I guess another projection down. These are just different projections of five cells, but basically a four-dimensional simplex. Now, as far as today's explanation goes, just to be able to visualize it, we will have a two-dimensional function, and our simplex will be a triangle, and you'll see how the Nelder-Mead method works there. Okay. All right. So we're going to say we have some arbitrary function that exists in two-dimensional space, and what we want to do is we want to find a local minimum. So we start with the vertices of our simplex, which will basically just be the corners of a triangle. And we take those and you just arbitrarily select the corners of your triangle. It really doesn't matter where. You just arbitrarily select them to form your simplex, and then you will do one or more of these steps. The first step you'll always do is sort, and then you will try reflecting the uh, the points, and then perhaps try an extension, maybe a contraction, maybe shrinking it. Um, you know, one of steps 2 through 5, and then once you use the algorithm to kind of select a new location, then you will check for convergence. If it hasn't converged, you will repeat, and you will keep going, sorting and then doing one of these uh, you know one of these operations here. Okay, so here is we'll go through each of these steps, and here's our starting triangle. Okay, my starting triangle looks like this. And what we do is we evaluate the function at the three corners. and we label them accordingly. So remember, we're looking for the minimum value. And so in our case, the location where the function has the lowest value is what we consider our best performing point. So here, the if the function at u is the least, and the function at w has the greatest value, then u is our best performing point, and w is the worst performing point. So in our kind of diagram, this corner over here has the lowest value. This is our best performing point. V is our second best, and W is our worst performing point. Okay, so we take our three vertices, we label them, we identify which one is the worst point. And what we want to do is we want to basically improve our simplex. We want to find basically another triangle that's an improvement. So at least basically we want to get rid of W and find a better performing point. Okay. So the first location we will check is going to be the reflected point. So we identify the worst performing point as W, and we reflect it through the center or the centroid of the remaining points. So in our case, with a triangle, the remaining points are just points U and V. We have a midpoint here, and we reflect W through the midpoint. So basically, you find the vector that takes W to the midpoint, and then you add that same vector to the midpoint to get your reflected point there. Okay? And we will evaluate the function at R. If you have um, if you have like a tetrahedron, okay, if you have a higher dimensional if you have a higher dimensional thing, then so let's say you have okay, why am I struggling so much to draw? All right, so let's say we have this triangle, and then this is our worst performing point here. Okay, this is W. So we would take the centroid of the 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 remaining 3 points, right? So if this is, points A, B, and C, we take the centroid of the remaining 3 points, and then that would basically, point over to here. Okay. So I don't know. Basically you have um you have a centroid, and you would reflect it through that centroid, and you would end up getting kind of another you have one tetrahedron, and then basically it's reflection. Okay. So we evaluate the cost at the reflected point, and if the cost at the reflected point is better than V, okay, so better than so then that would mean V becomes our worst point. Okay, if R is better than V but not better than U, then we will go ahead and take the reflected point. Okay, and after this change, then V becomes our worst performing point. And then we would check for convergence, and then we would repeat. Okay. So sometimes you just reflect, and then that's it, and you move on to the next iteration. Okay. If you reflect it, and the reflected point is even better than your best performing point. Okay. So R is now your best performing point. Then you say, you know what? We are really kind of moving in the right direction. And so we're going to press our luck a little bit, and we will try an extension. Okay. So, if this right here is my midpoint between U and V, um, basically I've added a vector, and I'm going to add basically one more of those vectors, right, from R, and that will take me down to E. Okay. So, if R is better than U, the algorithm basically tries to be a little bit greedy by trying something further in this direction. We're saying, you know what, the reflected point seems to be taking us in the right direction. So let's just push our luck a little bit and just try going even further in that direction. That takes us to the extended point. And we evaluate the function at the extended point. If the cost at the extended point is even better than the reflected point, then we will take the extended point and we'll replace the worst point with the extended point, and our new triangle, our new simplex will be U, V, and E. Okay. However, if you extend it and that's not better, like, the reflected point is the better point, is better than the extended point, then we will just take the reflected point and our new triangle will be UVR, okay? Where R is our best point and V is our worst point. So, if the reflection works, you might try extending it. Maybe you take the extended point, or maybe you don't, and you take the reflected point. If you try out the reflected point, and let's say the reflected point is not better than V, okay? So U is the best point, V is the second best, and you reflect it. And even if the reflected point is better than W, if it's not better than V, if the reflected point is your third best point, then you don't want it, okay? Because then at the next, like if you take it at the next iteration, this will be the worst performing point. R is going to be our worst performing point, and we would just reflect it again, and we would end up back at W. So we would just kind of be stuck in this uh, location where we're not getting any kind of improvement. So um, if R is not any better, then what we will attempt is we evaluate the two contracted locations. We have an inside contracted point and an outside contracted point, okay? See, the contracted point on the inside is basically a quarter of the way from W to R, or maybe halfway of the way between W and the midpoint. And then the outside contracted point is around 3/4 of the way from W to R, or halfway between the midpoint and R. And you evaluate the function at both of these contracted locations. And if either of these points perform better than V, okay, then we replace W with the better performing point. So you evaluate, maybe perhaps both contracted points are better than V, then you just take whichever one is the best, okay? Whichever one is the best performing of those things. Okay, again, check for convergence. And then repeat at the next iteration. Okay. And finally, if none of those locations work, so you tried reflecting it, you're not getting improvement. You tried contracting it, you're not getting improvement. Then in that case, you will just shrink your simplex. Okay. U is your best performing point, and so you will shrink the simplex down towards U. So you will replace W with W prime, a location halfway between W and U, and you'll replace V with V prime, a location halfway between V and U. Okay. And then you repeat the process there. So that is step 5, the shrinking. Um, and then after any of these things, you kind of check for convergence. And then you would repeat the whole process again. So how you check for convergence, there's a few different ways, but basically one is you can just see if one is you check your 3 locations, and basically if the difference between your best performing point and your worst performing point is very little, you can stop. You can also kind of check the standard deviation of the 3 locations, and if that is very little, you can also stop. And anyway, once you've reached some kind of location for convergence, then you will kind of take your best performing point, whichever point is your best performing point, and that will be your optimum location. Okay, I have a animated demo on YouTube that illustrates the Nelder-Mead algorithm. Okay. And so this, here, let me see. the simplex I'm going to start off with is going to be a triangle 0, 0, 0, 1, and 1, 0. So this is going to be my initial starting simplex. You start with an arbitrary simplex. We evaluate. The first thing we're going to do is we're going to evaluate our simplex and identify the worst performing point. Okay, so the worst performing point is this red dot. So every time I evaluate the simplex, I color in the vertices, and the worst performing point is going to be the red dot. Then the first thing we do is we try reflection. Okay, and so when I reflect this red dot across the midpoint, I end up over here. And looking at these contour lines, right? So this is our minimum is going to be around here, and we can see this location outperforms. Um, this over here is our best performing point, and this is our second best, and this is our worst. It outperforms even our best point. So with that, we're going to say, okay, well, we seem to be moving in the right direction. We'll try extending it. Okay. So we try extending it. Okay. And extending it ends up over here. The extended point performs even better than the reflected point. So we will accept the extended point, and to show that we've accepted a point, we color it green. And then we will, our new simplex will be these two blue points and the green point. Okay, so this is my new simplex. I evaluate the simplex, the three corners, and we can see this is my worst performing point, the red dot here. So we want to replace this with a better performing point. We'll first try reflecting it. Okay, and when I reflect it, okay, we can see the reflected point outperforms my second best point, okay? But it does not outperform this point. So you can see this dot over here is inside this contour line, and the reflected point is outside the contour line, okay? There's a question in the chat, how far do we know to extend? So basically, um, yeah, when you extend it, okay, so right here, basically, I have a vector from from the worst performing point to the midpoint. Okay. And I'm going to add that same vector to the midpoint to get to my reflection. And then if I add that same vector from the worst point to the midpoint to the reflection, then it ends up at my extension point. And yes, we would extend only once. Okay. I suppose you could try design another algorithm that says, if the extended point is even better, then, try extending it even further. But we don't. We just extend it once, and if that does out even better, then we just kind of stop it there. Okay, we don't push our luck even further. Okay, so so, this is where we are. Again, to get a reflected point, we go from the worst point to the midpoint, and we take that same vector, okay, and we add it to the midpoint to get me to the reflected point, okay? And so this reflected point outperforms the second best point, but not the best point. So we will replace the worst point with that. And so my new triangle will be these 3 points, okay? And this will be my worst performing point, okay? And so I will try reflecting it through the midpoint. So the midpoint is going to be right here. I take the vector that takes it here, and then I reflect it, and I will end up somewhere over here, okay? Or over here, I guess. And so when I reflect it, this point outperforms even the best point. So this is my, when I started off, this is my best, second best, and this is my worst point. When I reflect it, this outperforms even my best point. So I'm going to try extending it, and I extend it, and we end up over here. And when I look at the extended point, that does not do better than my reflected point. So I'm going to take the reflected point, and my new triangle will be the 2 blue dots and the reflected point. So this is the reflected point that I accept, and this is going to be my simplex. I evaluate again. This is now my worst point. I'm going to try reflecting it. And when I reflect it, we can see the reflected point outperforms my second best point, but not better than my best point. So I will take the reflection, and that becomes my simplex. This is now my worst point. So you can see that by kind of um, replacing the worst performing point with another point, our simplex or triangle kind of moves, and it moves towards the the minimum, right? It's kind of like playing it's almost like playing leapfrog, but you've got 3 points that you're dealing with, right? So we will try reflecting it. Okay, so I reflect it, and it's hard for me to tell if this reflected point performs better than this point or not. I guess it does, so we will take it, and this is going to be my simplex there. Okay, so this is going to be my worst point. I will try reflecting it. And when I reflect it, the reflected point does it does not do any better than the my current worst point. Okay, so this or doesn't do better than the second best point. So so now I'm going to try contracting it. I'm going to try the outside and inside contracted points, and evaluating the outside and inside contracted points, we will take the inside contracted point, which is halfway between the worst point and the midpoint, and that will be the location I select. Okay, there's a question in the chat. When evaluating the points, we just see which value is the lowest or highest based on we are looking for the minimum or maximum. So the algorithm is always written to find the minimum. So yeah, we're always looking for the best performing point, which is going to be the lowest value. Okay. Um, and the code is all written to uh, find the minimum. And so if you want to kind of maximize a function, you just basically take your function and multiply by -1, and then minimize that. Okay, so here is our the inside and outside contracted point. We look at this, and the inside contracted point performs better. So we will accept that. And my simplex looks like this. This is my worst point. I'm going to try reflecting it. When I reflect it, the reflected point does not outperform our either of our two inside points or two other points. So we'll try the outside and inside contracted points. And in this case, we can see the outside contracted point is going to perform better than the inside contracted point. So we will take that. And my simplex looks like this. This is my worst performing point. I'm going to try reflecting it. Okay. The reflected point does not improve. So we try an outside and inside contracted point, and the inside contracted point does better. So we will take that. Here is now my worst performing point is here. I try reflecting it. We can see the reflected point's not going to do any good. So we'll try the inside and outside contracted points. This contracted point is going to be the best. So now my simplex looks like this. I try reflecting it. That doesn't do well. So we contract, and this is what my resulting thing looks like. Here is my worst performing point. I try reflecting it. And when I reflected it, this performed better than any of the other points. So I'm going to try extending it. When I extended it, that did not improve things. So we will take the reflected point. Okay. I'm going to try reflecting. This is my worst performing point. We'll try reflecting it. That takes me over there. That doesn't work. We try contracting it. Okay. And this is the best of the contracted points. So now my simplex is getting smaller and smaller because we're doing a lot of kind of these contraction operations. We will try reflecting it this point, and the reflected point performs better than my second best point, but not better than the best point. So we will just take that. This is kind of my triangle here. Here's my worst performing point now. I reflect that. And that one doesn't do any better. So we try contracting the inside and outside, and we will take the outside contracted point. And so now we're getting pretty close to wherever the minimum is. And I guess this is my kind of better performing point, and I would contract it there. All right. So let me just show you the animation from the very beginning and just let it run. Okay, so we reflect, extend, take the extension. We reflect, take the reflection. Reflect, extend, we take the reflection. We reflect and we take the reflection. Reflect, take the reflection. Reflect, contract, take the contraction. Reflect, then contract, take the contraction. Reflect, then contract, and we take the contraction. We reflect, we contract again. Okay, we reflect and then we contract. We reflect and take the reflection, and reflect and then contract. So here, as we get closer and closer, we do a lot of kind of contracting. All right, so we contract our simplex, make it smaller, and this is just kind of like we're homing in on the kind of optimal location. So that is how the Nelder-Mead algorithm works. Let me give you your view quiz answers. Today, the answers are the letters A, B, and C. So A as in apple, B as in bear, C as in cat. A, B, C are your three view quiz answers for today. All right, today's lecture is a bit of a shorter one, but this is how the Nelder-Mead method works. This Nelder-Mead method is actually the default optimization method in R's optim function. So R has a general purpose optimization function. You provided another function and you say, I want you to find the minimum of this other function, and its default method is the Nelder-Mead method. There's other optimization algorithms you could use, but the default is Nelder-Mead, and this is an illustration of how the Nelder-Mead method works. And that will be it for today's lecture. Have a great rest of your day. I will have office hours later, starting at 10:30 here online, same link. And other than that, we'll see you Friday.